Hey, everybody. So, before I turn you loose on these amazing space-age graphics from the mechanical universe, I wanted to review really quickly some of the new formulas that we're talking about in Chapter 27. Chapter 17. What we're going to be looking at are gravitational and electric potential energy, and one of my favorite topics of all time, voltage, and also voltage. Now, the relationships that we're going to start with, when it comes to gravity, the potential energy of an object is mgh. We nailed that, last year. Voltage, on the other hand, is really just going to be the field strength times the distance. That would be if something has gravitational potential. It doesn't have potential energy until you put a mass there. Now, if we look over at the corresponding electrical explanation, if we talk about electric potential energy, it would be the charge placed in an electric field over a certain distance. The potential, the electric potential, also known as voltage, would be the electric field times that distance. Now, for point charges, which is what we're going to focus on a lot in this class, we can rewrite that as the potential equals K, Q times R. And it's important that if it's a positive charge, you put a positive Q in. It has positive potential. If it's a negative charge creating this potential, then it would have negative potential. So you got to use the signs. Okay. Now, before we get into the video and the graphics that they show us, I wanted to just review sort of in our gravity world, what lines of equipotential, sometimes pronounced equipotential, would mean. So here I am, standing with a ball above the floor. And let us assume, for the sake of argument, that the potential energy at the floor is equal to 0. What that means is that at any height h above the floor, the potential would be the same. Let's see, if I draw it there, or there, or there. Now, actually, cut. So let's go ahead and mark. Cut. So let's go ahead and mark the ground as being at potential energy equal to 0, or height 0. If I wanted to note what the voltage was at any point, I could go ahead and anywhere along this line that is the same height above this h equals 0, the voltage would be the same. If I place that green sphere in position 1, position 2, or position 3, it doesn't matter. Along this line, we would have equipotential. And that is true for any horizontal line that I draw in this diagram. So just drawing a horizontal line isn't enough. If I'm going to go ahead and draw a horizontal line like that, what I need to do is make sure that each separation of dotted lines are equal to the same thing. So everywhere along this line has the same potential. And if I were to space them perfectly and correctly, this change in voltage would be the same for each separation. If that's true, I could say that these lines of equipotential were drawn to scale. Now, let's take a look at a mountain. Here's a mountain off the coast of Alaska. So this would be at sea level. What we're looking at here is yeah, there it goes. That looks good. Now, lines of equipotential here, I would draw in sort of, boom, That could all be at the same height above sea level. Boom. Boom. And as long as they are evenly spaced, even as they pass over a gap, we would still be at equipotential positions. Now, I know some of you are going to ask, Mr. Edgar, did you mean to make those different distances? You know I didn't. You know I was doing my best to try to draw those evenly spaced. How does that look? Not great. So instead, how about we look at a contour map? Here we are, Mount Washington. And the key, as I feel like you should know, is that the key to reading a contour map is that each separation from line to line has to be equal to the same amount. It can't just be random, or else the contour map would be useless. So here we can see where these lines of equipotential are more closely spaced together, the steeper the terrain, where the more they are spaced out, the less steep the terrain. But what I would say is that all along this line, the height above sea level is the same. So anywhere along this line, the potential, the gravitational voltage would be the same.
On the surface, the electrical connection between Las Vegas and these Nevada hills isn't immediately obvious. For one thing, surveyors don't gamble. There's nothing random in the detailed precision of their maps, nor in their measurements that determine the height above sea level of each point on a predetermined grid. A line is drawn, connecting all points a certain height above sea level, and then repeated for other heights at regular intervals. To a practiced eye, the resulting contours of constant height give a clear representation of the real landscape. By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential, and they too represent a terrain that has its ups and downs. When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope. To put it in more mathematical terms, the electric field is a negative derivative of the potential. Or, in other words, the potential is minus the integral of the electric field. The electric field of a single point charge is proportional to 1 over r squared. So its integral is proportional to 1 over r. For a single point charge, the direction of the field is pretty obvious. But what about more complicated situations? What does the electric field for this potential look like? because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equipotential at every point. And that's how it assumes its familiar shape. The familiar shape of even the most rugged terrain isn't all peaks and valleys. Some regions are perfectly flat and horizontal. A lake is a region of constant height above sea level. Just as a region of constant electric potential is created by a conductor in an electric field. And since electric potential is the same everywhere on the surface of a metal, the electric field is always perpendicular to that surface.
All right, welcome back. So, you have to admit it. By the time we got to the end, those visuals were actually pretty cool. I wanted to take a moment, though, and make sure that you got the point. So I screen grabbed a few of those things, and I thought we could talk about them really quick. First of all, number one, the electric field lines are always going to be perpendicular to the equipotential lines at each point. And when we look at electric field lines, they're always going to point from a positive charge towards a negative. But if you look at every single place where the field lines are crossing these lines of equipotential, it's always going to hit perpendicular. It's beautiful, isn't it? It's beautiful. All right, so that's the first thing. The second thing I thought was really pretty important. They buzzed right through this in the last 45 seconds, and it said, in a solid conductor placed in an electric field, the electric field inside the conductor is zero. Therefore, the potential, the voltage, is always going to be constant. Now, they just brushed right through the fact that the electric field would be zero. I wanted to take a moment and make sure I hit on that a little bit. So I went and drew in an electric field, and an electric field would have a number, say, I don't know, how about 400 newtons per every coulomb. And if I go ahead and take a solid conducting sphere, now it's a conducting sphere, which means it's made most likely out of some metal, which means that the very outermost electrons are barely held to the nucleus, and they can easily be forced to move. Now, if I take that sphere and I place it, this is a sphere, not a circle, and I place it in the electric field, that electric field is going to cause some of the charges to move. In fact, what it'll do is it will cause the negative charges to move against the field and start to collect on this side of the sphere. That will leave behind positive charges, like an outgoing tide leaves those poor barnacles hanging out. And because of that charge separation, what ends up happening is that the electric field that's caused inside the conductor will be exactly opposite the electric field from outside the conductor, and they cancel out. So that inside, let me try this again. Inside, the electric field goes to zero. Yeah. If there was still an electric field, then the charges would keep moving. Okay? So once it reaches a static equilibrium, there's no field inside. If there's no electric field inside, then the potential is going to stay constant. Then I jump to this picture here. So here we have something similar to the picture they showed us before, but this time it's got flat top, like plateaus, if you will. What we're really looking at in this really cool picture is an area of equipotential right here where it's staying the same. And if we take that and instead of looking at it at an angle, look at it in just the X and Y directions, we have a graph that looks something like this. So there the voltage is constant would be across that entire material conductor. By the same token, the negative potential would also be constant throughout. And our curve is going to look a little something like this. Okay, where at the center, the voltage or potential would be 0. Now, the electric field is not 0 there. That's where it gets a little tricky, but that's for another day. Okay, so what we're looking at here in this diagram is a cool sort of 2D representation, maybe even 3D representation of this. All right? The whole point of that video is to the last 3 minutes. I want to make sure you caught it. I hope you guys are doing okay. In just a bit, I'm going to put you on working on a pet activity where hopefully just experimenting with some of the numbers and moving things around will help you get that picture in your head of what we're really talking about. Okay? Hang in there, everybody. Thanks. Zip.